You don't begin this story with a photograph. There is no glowing nebula, no spiral galaxy, no dramatic pillar of gas. What begins this story is a pattern thin, statistical, almost shy, emerging from light that has traveled for more than 9 billion years, far out in the universe, at a time when Earth did not yet exist. Astronomers noticed something unsettling, not an object, but an arrangement, a curved alignment, a suggestion of geometry where geometry was never expected. It looked, uncomfortably, like a ring. Not a ring you could point a telescope at, not a ring you could circle in red, but a structure inferred from absence, from tiny dips in the brightness of distant quasars, as if something immense was quietly standing in front of the light, leaving only its shadow behind. The size of this inferred shape was staggering, roughly 1.3 billion light-years across. To put that in perspective, light itself, moving at the fastest speed allowed by the universe, would need more than 1 billion years just to cross from one side to the other. Entire clusters of galaxies could drift inside that span, like dust motes in a cathedral, and the distance was worse. This structure appeared to sit 9.2 billion light-years away, meaning the universe was less than half its current age when the light carrying this information began its journey. You are not seeing it as it is now. You are seeing it as it was, when the cosmos was younger, denser, and supposedly simpler. That word supposedly matters, because according to the most basic expectations of cosmology, shapes like this should not exist. On the largest scales, the universe is meant to smooth itself out. Small irregularities are allowed. Clumps form. Galaxies gather into clusters, clusters into filaments. But beyond a certain size, everything should average away. No preferred directions, no giant curves, no billion light-year circles etched into space like cosmic graffiti. Yet here it was, a suggestion that the universe, at least once, may have ignored that expectation. The structure would later be called the Big Ring. The name sounds casual, almost harmless, but what it represents is not. Because once you notice a shape at that scale, you can't unsee it. The question is no longer what is it, but why is there a shape at all? In everyday life, shapes imply boundaries. Circles imply containment. Arcs imply curvature, motion, intention. Your brain is trained to read meaning into geometry. A ring is never just a ring. It suggests organization. It suggests process. That instinct is dangerous in cosmology. The universe is under no obligation to match human intuition. And yet, human intuition is exactly what must be confronted here. Because this is not a story about certainty. It is a story about tension between what the universe appears to show and what our theories insist should be true. To understand why this discovery feels so disturbing, you have to appreciate how indirect it is. No telescope ever resolved the Big Ring directly. What astronomers actually observed were thousands of distant quasars, brilliant, energetic cores of galaxies shining like lighthouses across the cosmos. As their light traveled toward you, it passed through clouds of gas scattered between galaxies. Some of that gas absorbed very specific wavelengths of light, leaving fingerprints, dark absorption lines embedded in the quasar spectra. These fingerprints were not dramatic. They were subtle, statistical, easy to miss. But when researchers mapped where those absorption signals appeared in space, something unexpected emerged. The absorbers were not evenly scattered. They clustered, and not randomly. They traced a curve, a vast, curved alignment, too coherent to ignore, too large to dismiss easily. At first glance, it almost feels like a trick of perspective. After all, humans are excellent at finding patterns even when none exist. You see faces in clouds, shapes in static, meaning in coincidence. Scientists are trained to resist this instinct, but they are still human. And yet, this pattern persisted across analyses, different subsets of data, different statistical tests. The ring-like geometry refused to dissolve. The unease deepened when researchers realized something else. This was not the first time such a structure had appeared, years earlier. Another enormous alignment had been reported at a similar distance, the giant arc, stretching across billions of light-years like a scar in the fabric of the universe. It, too, was inferred from absorption patterns. It, too, lived at roughly the same epoch in cosmic history. One anomaly can be dismissed as noise. Two anomalies, near each other in both space and time, begin to feel like a message, or at least a warning. But science is not built on feelings, it is built on restraint. So the discovery of the Big Ring did not arrive with celebration. It arrived with caution, with qualifiers, with footnotes and careful language. Researchers were explicit about uncertainty. They emphasized the need for independent confirmation. They acknowledged statistical pitfalls. Still, the question lingered. If the universe really is smooth on the largest scales, why does it appear to be sketching curves? You might be tempted to jump to dramatic conclusions, to imagine new physics, exotic processes, hidden forces shaping matter into colossal loops. But cosmology does not move that fast. Before rewriting textbooks, scientists interrogate the data mercilessly. And yet, even that interrogation reveals something profound, because whether the Big Ring is real or not, it exposes a fragile boundary in our understanding, a place where theory, observation, and interpretation collide. If it is real, then the universe may allow coherent structures on scales larger than previously thought, forcing a re-examination of how matter evolved in the early cosmos. If it is not real, then it highlights something equally important: the limits of statistical inference when mapping a universe we can never observe directly, only through echoes and shadows. Either way, the comfort of certainty dissolves. What remains is the image faint, inferred, controversial, of a universe that may not be as indifferent to structure as we once believed. Or worse, a universe that reflects our own tendency to see order where none exists. Standing here, at the edge of that ambiguity, you are reminded of something essential. Cosmology is not a collection of answers. It is a disciplined way of living with questions. Questions so large that even 1 billion light-years feels like a unit too small to contain them. The Big Ring does not shout. It does not glow. It does not announce itself. It simply appears quietly, mathematically asking whether the universe is truly as simple, as smooth, and as well-behaved as we hoped. And in that silence, something shifts. Before you can understand why a structure billions of light-years wide is unsettling, you have to confront a quieter problem, one that hides in plain sight. You have to understand what it means to measure something you can never reach. In everyday life, distance feels intuitive. You walk across a room, you drive across a city, you fly across a continent. Even the largest distances you normally encounter still fit inside a single human lifetime. They scale with effort, fuel, time. Cosmic distance does not. When astronomers say something is far away, they are not speaking metaphorically. They are describing separations so vast that ordinary units collapse under their own meaning. Kilometers become useless. Miles become laughable. Even the idea of travel itself starts to lose coherence. This is why astronomy abandoned familiar measures early on. Instead of asking how far something is in space, astronomers ask how long light has been traveling to reach you. That unit, the light year, is not a measure of time, but of distance. It is the span light covers in 1 year, racing through the vacuum at about 300 0.000 kilometers per second. Over the course of a year, that adds up to roughly 9.46 trillion kilometers. That number is already beyond intuition, but it is only the first rung on the ladder. Light from the sun reaches Earth in about 8 minutes. That seems manageable. A brief delay, a reminder that even sunlight is not instant. Light from the moon takes about 1.3 seconds. A cosmic blink, light from Mars, at its closest approach, takes around 4 minutes. At its farthest, more than 20, still. All of this exists comfortably within the solar system, a tiny bubble carved out by one ordinary star. Beyond that bubble, intuition begins to fracture. The nearest star system to the Sun, Proxima Centauri, lies about 4.24 light-years away. That doesn't sound far until you realize that even at the fastest speeds humans have ever achieved, a journey there would take tens of thousands of years. 4 light-years is already a wall. Now scale up. Our home galaxy, the Milky Way, spans about 100,000 light-years from edge to edge. Light itself needs 100 millennia to cross it. Every star you see in the night sky belongs to this single island of matter, floating in an ocean of darkness. Beyond the Milky Way lies Andromeda, the nearest large galaxy, roughly 2.5 million light-years away. Its light began traveling toward you when early human ancestors were just learning to walk upright. And beyond Andromeda are thousands of other galaxies, then millions, then billions. At this point, even the light year feels inadequate. So astronomers reach for deeper tools, not just new units, but new ways of thinking. One of those tools is redshift. As the universe expands, space itself stretches. Light traveling through that expanding space is stretched along with it, shifting toward longer, redder wavelengths. The more distant an object is, the more its light has been stretched. Redshift becomes a proxy for distance. Not perfect, not direct, but powerful. It tells you not just how far something is, but how old the universe was when that light was emitted. This is where distance and time collapse into one another. When you observe something 9.2 billion light-years away, you are not simply looking across space. You are looking back across time into an era when the universe was only about 4.5 billion years old. You are not seeing where it is. You are seeing where it was. That distinction is not poetic. It is fundamental. Cosmology is not the study of the universe as it exists now. It is the study of frozen moments, layered on top of one another, each carried forward by light at a finite speed. Every observation is an archaeological dig. This makes cosmic measurement profoundly indirect. You cannot stretch a ruler between galaxies. You cannot triangulate with tape and angles the way you might on Earth. Instead, you infer distance from brightness, color, spectral fingerprints, and statistical relationships. Every step relies on assumptions tested, refined, but never absolute. This is why scale matters so much. A structure a few million light-years across is expected. Filaments and clusters naturally emerge as matter responds to gravity over cosmic time. But a structure over 1 billion light-years wide exists in a different regime altogether. At that scale, the universe is supposed to forget its local irregularities. The clumps average out. The curves flatten. The statistics smooth themselves into near uniformity, not because the universe prefers simplicity, but because randomness, over vast enough volumes, cancels itself. This expectation is not aesthetic, it is mathematical. It underpins how cosmologists simulate the universe. It underlies how they interpret surveys. It is woven into the logic that allows a limited set of observations to say something meaningful about everything, which is why numbers like 1 billion light-years carry weight beyond shock value. They push directly against the boundary where theory says structure should fade into noise. And here is where the human mind struggles again. 1 billion is not just a large number. It is a scale that resists emotional comprehension. Your brain does not feel the difference between 1 million and 1 billion the way mathematics does. They blur together, but physics does not blur. At these scales, tiny deviations matter. Small statistical fluctuations become arguments. Slight biases in measurement can inflate into apparent structures. This is the tightrope cosmology walks. When astronomers claim something is extraordinarily large, they are not merely impressed. They are cautious. Because large claims rest on long chains of inference, each link vulnerable to misinterpretation. To measure the unimaginable is not to conquer it. It is to admit dependence on light, on models, on probability, and yet, without this fragile scaffolding, nothing beyond the solar system would be knowable at all. Every galaxy you've never seen, every structure you'll never visit, every era that ended billions of years before Earth formed exists for you only because photons survived an impossible journey and arrived with just enough information intact. That is what makes discoveries like the Big Ring so unsettling. They are not measured with confidence born of proximity. They are measured at the extreme edge of what inference can tolerate, at distances where the universe itself becomes the measuring instrument and the source of uncertainty. To speak meaningfully about such scales requires humility, not the humility of smallness, but the humility of method, the understanding that every cosmic measurement is provisional, conditional, and deeply entangled with the assumptions that make it possible. You are not standing outside the universe, measuring it from afar. You are inside it, trying to reconstruct its shape from whispers of ancient light. And sometimes, those whispers sketch forms too large, too coherent, to ignore. Not because you fully understand them, but because you understand just enough to know how fragile your certainty really is. You might imagine astronomy as an act of seeing, of capturing light, freezing it into images, and pointing to what exists. But much of the universe refuses to cooperate with that picture. Some of its most important structures do not glow. They do not shine. They announce themselves only by what they take away. To understand the invisible universe, you have to unlearn the idea that seeing means illumination. In deep space, absence can be louder than presence. Consider the quasar. From a distance, it looks like a star, but it is anything but. A quasar is the blazing core of a distant galaxy, powered by a supermassive black hole devouring matter at a furious pace. As gas spirals inward, it heats to extraordinary temperatures, releasing energy so intense that a single quasar can outshine an entire galaxy. These objects are visible across billions of light years. They are among the brightest beacons the universe has ever produced, and that brightness makes them useful in a way that feels almost accidental, because as quasar light travels toward you, it does not move through empty space. It passes through clouds of gas drifting between galaxies' thin, cold, unremarkable regions of matter that would be invisible if not backlit. When quasar light passes through these clouds, specific wavelengths are absorbed by atoms in the gas. The result is a set of dark lines carved into the otherwise smooth spectrum of the quasar's light. These are absorption lines. They are not images of objects. They are fingerprints, evidence that something stood in the way. Among the most important of these fingerprints come from ionized magnesium, known as Mg2. Magnesium atoms absorb light at very precise wavelengths. When astronomers detect these absorption signatures in quasar spectra, they know that a cloud of gas rich in magnesium lays somewhere along the line of sight. Each detection marks a location in space, not a pinpoint, but a region where matter exists. Now imagine repeating this process not once, but thousands of times. Thousands of quasars scattered across the sky, thousands of lines of sight piercing the universe at different angles and depths, each one leaving behind a trail of absorption clues. On their own, These detections mean very little. Isolated. They look like noise, random specks on a cosmic map, but when enough of them are plotted together, patterns can emerge, not because the universe wants to be seen, but because statistics eventually expose structure. This is where the invisible universe begins to take shape. Astronomers do not see filaments of gas directly stretching across space. Instead, they notice that absorption signals cluster in certain regions and thin out in others. They notice alignments, correlations, unexpected coherence. It is like mapping a city at night by watching which streetlights flicker when fog rolls in. You never see the streets, you infer them from interruption. This method is powerful and dangerous. Powerful because it allows scientists to probe regions of the universe that emit almost no light. Dangerous because it relies on interpretation, on thresholds, on decisions about what counts as significant. Every map of the invisible universe is built on choices. How strong must an absorption signal be to count? How close must detections lie to be grouped together? What statistical model defines random? Change those choices slightly, and patterns can sharpen or dissolve. This is why claims about enormous structures inferred from absorption data are always met with scrutiny. The data does not shout. It whispers, and whispers can be misheard. Still, some patterns persist. When astronomers analyzed large catalogues of Mg2 absorbers, they noticed something unexpected. The absorbers were not evenly scattered. They did not form a smooth, uniform haze. They traced out curves, not perfect circles, not sharp boundaries, but arcs, partial rings, long, coherent stretches where the probability of finding absorbers rose far above chance. The geometry was not imposed, it emerged, and emergence is the most unsettling kind of discovery because it resists easy dismissal. If this were a bright object, a galaxy, a cluster, it could be photographed, measured, debated visually. But an inferred structure has no edges you can point to, no single image you can dispute. All you can do is argue over statistics. Is this alignment meaningful, or just the inevitable byproduct of surveying a vast universe with limited tools? This question sits at the heart of modern cosmology. The universe is too large to observe directly in its entirety. Every map is incomplete. Every survey samples only part of the sky, only certain distances, only certain types of matter. And yet, from these fragments, scientists attempt to reconstruct the whole. The invisible universe forces humility because it exposes the scaffolding behind discovery. It shows you the assumptions, the approximations, the leaps of faith that turn raw data into cosmic narratives. There is something deeply human about this process. You cannot step outside the universe to see it from above. You are embedded within it, peering outward through narrow windows, trying to infer vast structures from the faintest hints. The invisible universe is not empty. It is full of gas, of dark matter, of subtle gravitational influences. But it does not reveal itself easily. It must be coaxed into visibility through patience, mathematics, and restraint. When a structure like the Big Ring is proposed, it is not because someone saw a glowing loop in the sky. It is because countless invisible interactions spread across billions of years and light years, lined up just enough to suggest coherence. That suggestion is fragile. Remove a subset of data, change a statistical assumption, expand the sample, and the shape may blur, but the fact that it appeared at all matters, because it reminds you that much of the universe exists beyond direct perception, that what you see, stars, galaxies, nebulae, is only a thin veneer over a much larger, quieter architecture, and that architecture does not care how you expect it to behave. Seeing the invisible universe requires a different kind of vision, not eyes, but inference, not certainty, but probability, not images, but patterns traced through absence. It is a way of knowing that never feels complete, which is why discoveries at this frontier feel so unsettling. They are not declarations. They are questions written in data, questions that ask whether the universe truly smooths itself out at grand scales, or whether it hides structures so subtle that they only reveal themselves when light passes through them, billions of years later, leaving behind nothing but shadows. And sometimes, when enough shadows align, the darkness begins to outline something immense. At some point, every cosmological story runs into an assumption so basic that it often goes unspoken, an idea so foundational that it feels less like a hypothesis and more like a quiet promise about how reality behaves. The promise is this: on the largest scales, the universe is smooth, not empty, not featureless, but statistically even. No preferred directions, no special places, no gigantic patterns that dominate everything else. This idea is known as the cosmological principle, and without it, modern cosmology would collapse under its own complexity. The principle does not claim that the universe looks smooth up close. Clearly, it does not. Galaxies cluster, stars form in groups, matter gathers into filaments, walls, knots. On smaller scales, the universe is lumpy, chaotic, richly structured, but zoom out far enough. And those irregularities are supposed to cancel each other out. Like the surface of the ocean, from a boat, the sea is violent waves, peaks, turbulence. From an airplane, it becomes textured but coherent. From orbit, it smooths into a nearly perfect curve. The details disappear. The average remains. Cosmology assumes the universe behaves the same way. This assumption is not aesthetic. It is practical. Without it, you could never generalize from what you observe locally to what exists elsewhere. You could never say that a patch of sky represents the universe as a whole. Every measurement would apply only to itself, and nothing more. The cosmological principle is what allows scientists to simulate the universe, to test theories, to connect the physics of the early cosmos with the structures seen billions of years later. It is the reason cosmology is possible at all, but it is also an assumption born of necessity, not certainty. No one can step outside the universe to verify it. There is no external vantage point. There is only observation from within, constrained by light speed, cosmic horizons, and finite data. The principle works because, so far, it has worked well enough. Maps of the cosmic microwave background show remarkable uniformity, with temperature variations of only 1 part in 100,000. Large galaxy surveys reveal filaments and voids, but when averaged over hundreds of millions of light-years, the distribution approaches statistical homogeneity. The universe, it seems, behaves up to a point. That point is where structures like the giant arc and the big ring become uncomfortable, because they live precisely in the regime where smoothness is supposed to win. 1 billion light-years is not a casual scale. It is not a large cluster. It is not even a supercluster. It approaches the scale at which cosmologists expect the universe to forget its local history, to erase the memory of initial fluctuations and settle into near uniformity. At those distances, any structure that remains coherent is not just impressive, it is suspicious, not because it is impossible, but because it strains the statistical logic that underpins the cosmological principle. If matter clumps too strongly on those scales, then either the universe began with more structure than expected, or something later amplified those clumps in ways not fully captured by current models. Neither option is comfortable. The first challenges assumptions about the early universe about inflation, quantum fluctuations, and the origin of cosmic structure. The second suggests gaps in how gravity and matter interact over immense distances. But before either conclusion can be taken seriously, a harder question must be faced. What does smooth actually mean? Smoothness in cosmology is not visual. It is statistical. A region is considered homogeneous not because it looks featureless, but because the distribution of matter within it matches expectations when averaged appropriately. This means that smoothness depends on scale. A region that appears highly structured at 100 million light-years may appear smooth at 1 billion. The choice of scale is not arbitrary, but it is crucial. Too small, and everything looks chaotic. Too large, and meaningful features dissolve. The cosmological principle asserts that there exists a scale beyond which the universe becomes statistically uniform. The challenge is identifying where that scale truly lies, and that is where disagreement begins. Some analyses suggest homogeneity emerges around a few 100 million light-years. Others place it closer to 1 billion. The exact value depends on methodology, data selection, and definitions. This uncertainty creates a narrow corridor where anomalies can live. Structures that sit just at the edge of the expected homogeneity scale are neither clearly forbidden nor comfortably allowed. They exist in a gray zone large enough to raise eyebrows, small enough to avoid outright contradiction. The Big Ring occupies this zone. Its reported size does not immediately shatter cosmology, but its geometry, a curved, ring-like arrangement, adds an extra layer of unease. Because smoothness is not just about size, it is about isotropy. A universe that is smooth should not prefer shapes. It should not draw arcs. It should not trace circles across billions of light-years. Patterns of that kind suggest coordination, and coordination implies correlation. And correlation, at extreme scales, is precisely what smoothness is meant to erase. Yet the universe is under no obligation to satisfy human definitions. The cosmological principle is a working assumption, not a law of nature. It is embraced because it simplifies, not because it has been proven in every possible regime. This distinction matters. When data challenges the principle, cosmologists do not panic. They test. They replicate. They question methods. They ask whether the anomaly is real, or whether it emerges from how the data was collected and interpreted. Because history offers a warning, time and again. Apparent violations of cosmic order have dissolved under better measurement. Structures once thought extraordinary later revealed themselves as artifacts of incomplete surveys or biased sampling. The universe has embarrassed theorists before, not by being stranger than imagined, but by being less strange than claimed. And yet, occasionally, the opposite happens. Occasionally, an anomaly survives scrutiny and forces revision. The expansion of the universe was once an anomaly. So was dark matter. So was dark energy. Each began as an uncomfortable mismatch between expectation and observation. The difference is subtle but crucial. Not every challenge reshapes theory, but every reshaping of theory begins with a challenge. The cosmological principle has survived a century of scrutiny because it adapts. It allows for structure, but only up to a point. It tolerates irregularity, but insists on balance in the end. What makes the Big Ring unsettling is not that it violates this principle outright, but that it approaches the boundary where tolerance ends. It forces cosmologists to ask, how smooth is smooth enough? That question has no easy answer, because the universe is not obligated to conform neatly to our categories. It evolves. It remembers. It carries imprints of its past forward in ways that statistics sometimes struggle to erase. A universe that was supposed to be smooth may still harbor echoes faint, enormous, and difficult to interpret. And when those echoes take the form of curves across billions of light years, the promise of smoothness begins to feel less like a guarantee and more like an approximation, one that works until it doesn't. Standing at that threshold, cosmology does not collapse. It pauses, and in that pause, the universe reveals what it has always been, not a finished picture, but a negotiation between expectation and evidence. played out on the largest canvas imaginable. Before humans could argue about rings 1 billion light-years wide, they had to solve a much humbler problem. They had to learn how to tell how far away anything was at all. For most of history, the sky offered no distances, only directions. Stars rose and set. Planets wandered. The heavens appeared fixed to a dome, equally far, equally unreachable. Near and far were earthly ideas. The cosmos had no depth. The first crack in that illusion came from geometry. More than 2,000 years ago, Hipparchus realized something subtle but powerful. When you change your position, nearby objects shift slightly against distant ones. Hold out your thumb and close one eye, then the other. The background jumps. Your thumb moves. That shift parallax could, in principle, measure distance. On Earth, it works beautifully. In the sky, it almost doesn't work at all. Stars are too far away. Their parallax angles are tiny fractions of a degree, then fractions of fractions. For centuries, astronomers searched for stellar parallax and failed. Some took this as evidence that Earth did not move. Others took it as evidence that the stars were unimaginably distant. They were right about the second part. It wasn't until 1838 that parallax finally yielded. Friedrich Bessel measured a shift of just 314 arcseconds in the star, 61. Cygni, an angle so small, it's like seeing a coin move the width of a human hair from kilometers away. That measurement did more than fix a distance. It broke the sky open. For the first time, a star was no longer a point on a sphere. It occupied a place in three-dimensional space. The universe had depth. From that moment, astronomy became a ladder. Each rung relied on the one below it. Parallax gave distances to nearby stars. Those stars could then be used to calibrate brighter objects, standard candles, whose intrinsic brightness was known. If you knew how bright something truly was, and how dim it appeared, distance followed. Among the most important of these candles were Cepheid variable stars. Their brightness rises and falls in a precise rhythm, and the period of that rhythm is tightly linked to their true luminosity. Measure the pulse, infer the brightness, calculate the distance. This relationship transformed astronomy from mapping points to mapping volumes. Then came the moment that shattered humanity's cosmic ego. In the early 20th century, Edwin Hubble used Cepheids to measure the distance to a fuzzy spiral in the sky Andromeda. It was not nearby. It was not part of the Milky Way. It was an entire galaxy of its own. The universe, once thought to be a single island of stars, suddenly became an archipelago, millions. Then billions of galaxies drifting apart in darkness. Distance did not just expand, meaning did. Hubble's work led to another revelation. Galaxies farther away appeared to be moving away faster. Space itself was expanding. Distance and motion became inseparable. To measure how far something was now meant measuring how fast the universe had stretched since its light was emitted. The ladder grew taller and shakier. Beyond Cepheids, astronomers relied on supernovae, galaxy brightness correlations, and eventually the large-scale structure of the universe itself. Each step reached farther, but each introduced new assumptions. By the time distances reached billions of light-years, direct measurement was no longer possible. Astronomers were no longer measuring space alone. They were measuring history. Light arriving today carried timestamps from the deep past. The farther it traveled, the earlier the snapshot, distance became look-back time. This is why cosmic distance is never just a number. It is an inference layered on inference, built from relationships, discovered nearby, and extended outward with care. Every rung of the ladder rests on calibration, and every calibration rests on trust. Trust that the universe behaves consistently across space and time. That trust has usually been rewarded. But it also means that cosmic distance is never felt. It is calculated. You do not sense that Andromeda is 2.5 million light-years away. You do not intuit that the observable universe spans about 93 billion light-years in diameter. These facts live only in equations and comparisons are fragile things. They depend on context. When astronomers talk about something being too large, they are not reacting emotionally. They are reacting because the ladder strains under the weight. Because the inferred scale approaches the limits where averaging is supposed to work, where structure is supposed to dissolve. This is why the history of measuring distance matters so much, because it reminds you that cosmology is not built on direct experience. It is built on a chain of reasoning that extends outward from Earth, step by careful step. Each link tested against the last. Break one link, and the outer rungs wobble. And yet, without this ladder, nothing beyond the solar system would be knowable. The universe would collapse back into a flat sky of lights with no depth. No story, no evolution. Humanity learned to measure cosmic distance not because it was easy, but because it was necessary. Necessary to understand where we are. Necessary to understand when we are. Necessary to place meaning inside a universe that does not volunteer it. The ladder is imperfect. It always has been. But it is the reason a faint absorption line, buried in quasar light from 9 billion years ago, can be discussed at all. It is the reason a suggestion of a ring too large, too coherent, can unsettle modern cosmology. Not because humans have finally mastered distance, but because, after centuries of effort, we have mastered it just enough to know when something feels wrong. Long before anyone spoke about a ring, there was a line. Not a line you could draw on a photograph, not a filament glowing against the dark, but a vast, improbable alignment inferred from the same quiet clues, absorption signatures embedded in ancient light. It came to be known as the giant arc. At first, it didn't announce itself as a problem. It arrived the way many anomalies do, as a statistical curiosity buried in a technical analysis, easy to overlook unless you already knew where to look. Researchers mapping magnesium absorption systems across the sky noticed something unusual. Instead of scattering evenly, a significant number of detections appeared to cluster along a long, curved path. The span was immense, billions of light-years from end to end. That number alone was unsettling, but not decisive. The universe is large. Large things happen in large spaces. What mattered was not just the size, but the coherence. This alignment did not dissolve when the data were sliced differently. It did not vanish when thresholds were adjusted within reasonable bounds. It persisted as a statistically significant feature, stretching across a region of the universe observed as it was more than 9 billion years ago. At that distance, the universe was young, not newborn but still early in its long evolution. Galaxies were forming rapidly. Structures were assembling. Matter had not yet fully settled into the web-like patterns familiar today. This context matters. In a younger universe, large coherent structures are harder to explain. There has been less time for gravity to pull matter together across vast distances. Less time for small fluctuations to grow into large patterns, which is why the giant arc felt like a warning sign, not a contradiction, not a refutation. A warning. It whispered that something might be happening near the edge of what cosmology comfortably allows. The reaction within the scientific community was cautious. No headlines declared the end of cosmology. No textbooks were rewritten. Instead, the discovery was treated as provisional, interesting, but requiring confirmation. This restraint was deliberate. Cosmology has learned, the hard way, that extraordinary patterns can emerge from ordinary causes. Survey geometry can imprint shapes onto data. Selection effects can exaggerate alignments. Statistical noise can masquerade as structure if you search long enough. The universe is large enough that coincidences are inevitable. So the giant arc was held at arm's length, but it lingered. What made it especially uncomfortable was not just its size, but its shape. A long arc implies curvature. Curvature implies correlation across vast distances. It suggests that regions separated by hundreds of millions of light years are somehow linked, not causally. But statistically, and at these scales, correlation is exactly what the cosmological principle is meant to erase. To understand why this mattered, imagine scattering grains of sand across a beach. Up close, you see clusters, small piles, local irregularities. But from far away, the beach looks uniform. No arcs, no rings, no preferred directions. The giant arc suggested that, at least once, the cosmic beach might not be so even. Still, one anomaly can be tolerated. Cosmology is robust because it expects outliers. Given enough data, something will always sit at the edge of expectation. The key question is whether the outlier stands alone. For years, the giant arc did. It was cited cautiously, discussed quietly, filed under interesting but unresolved. Some researchers argued it could be a statistical fluke amplified by survey boundaries. Others suggested it might represent an extreme, but not forbidden, realization of cosmic structure. The debate remained open. What the giant arc did, more than anything else, was change how people looked at the data. Once you've seen a pattern, you begin to ask sharper questions. You test assumptions more aggressively. You wonder whether other structures have been hiding in plain sight, not because they weren't there, but because no one expected to find them. The giant arc shifted expectations. It encouraged researchers to examine absorber catalogues not just for density, but for geometry, not just for clustering, but for alignment. And that shift would matter, because the giant arc did not arrive as a declaration that cosmology was wrong. It arrived as an invitation to look again more carefully, more skeptically, more creatively. There is something important about that posture. Science does not progress by chasing every anomaly with equal enthusiasm. It progresses by learning which anomalies deserve patience, which ones survive repeated attempts at dismissal, which ones refuse to disappear. The giant arc refused to disappear entirely, even as debates continued, even as alternative explanations were explored. It remained a legitimate feature in the data, uncomfortable, unresolved, but present, and it carried with it a quiet implication. If one such structure exists at that distance, the probability of finding another nearby in cosmic time might not be negligible. That implication was not a prediction. It was a suspicion, a sense that the universe, when probed deeply enough, might reveal more coherence than theory had prepared us for. The giant arc became a reference point, not a smoking gun, but a marker. A reminder that the line between expected structure and problematic structure is thinner than it appears. It showed that the cosmological principle, while powerful, is not immune to challenge. It is an assumption constantly tested by data, not a shield against surprise. And perhaps most importantly, the giant arc taught cosmologists how to sit with uncertainty. It did not demand resolution. It demanded honesty about what was known, what was inferred, and what remained ambiguous. In that sense, it served its role perfectly. It did not overthrow a model. It did not rewrite a theory. It simply stood there, vast and curved, embedded in ancient light, reminding those who noticed it that the universe is not obligated to organize itself according to our comfort. Sometimes, the first sign of trouble is not a contradiction, but a shape that lingers just long enough to make you uneasy. The giant arc was that shape, and once it had been seen, the universe did not look quite as smooth as it once had. If the giant arc was a warning sign, the big ring was escalation. One immense structure could be absorbed into uncertainty. 2. Appearing in the same distant epoch of the universe could not be ignored so easily. The moment researchers realized that another large-scale pattern occupied roughly the same region of cosmic history, the conversation changed quietly, but decisively. This was no longer about an isolated anomaly, it was about repetition. The Big Ring did not announce itself as a dramatic breakthrough. It emerged from the same kind of data, the same method of inference, the same careful statistical treatment used before. Quasar absorption systems, again dominated by magnesium, were mapped across the sky. Their positions were analyzed not for brightness, not for mass, but for geometry. And this time, the geometry curved back on itself, not into a perfect circle. The universe rarely draws with precision, but into a structure unmistakably ring-like, an arc bending far enough, long enough, to suggest closure, a loop hinted at by absence rather than presence. Its scale was staggering, roughly 1.3 billion light-years in diameter. To comprehend that number, forget galaxies, forget clusters. Even superclusters strain under it. A structure this large approaches the scale where cosmology expects randomness to dominate, where coherence should dissolve into statistical fog. Instead, the Big Ring appeared coherent. What made this especially unsettling was not just its size, but its location in time, like the giant arc. The Big Ring appeared at a redshift corresponding to more than 9 billion years ago. This placed both structures in a universe still assembling its large-scale architecture. There had not been enough time, according to standard models, for matter to organize itself so extensively across such distances. Gravity works patiently, but not infinitely fast. Small fluctuations grow first. Larger ones take longer. The largest structures should emerge last, smoothed by expansion, diluted by randomness. Yet here was a structure demanding patience the universe may not have had. The stakes rose because coincidence began to feel strained. 2 immense patterns, similar distance, similar method of detection, similar defiance of expectation. This was no longer a single roll of the cosmic dice. It was at least a second, and probability cares deeply about repetition. At this point, the scientific response remained disciplined. No rush to claim new physics, no sweeping conclusions. Instead, the focus sharpened on interpretation. Was the Big Ring truly a structure, or a statistical mirage? Was it independent of the giant arc, or part of a larger, poorly understood configuration? Was the apparent ring shape meaningful, or simply the way sparse data projected onto a curved sky? These questions mattered because cosmology lives and dies by statistical integrity. When dealing with data sets that span billions of light years and millions of objects, patterns will always emerge. The challenge is deciding which ones matter. The Big Ring forced that challenge into the open, because unlike a linear alignment, a ring-like geometry triggers instinct. Circles are rare in nature at cosmic scales. They imply symmetry, balance, enclosure. Even when incomplete, they suggest intent. And intent is precisely what cosmology is trained to avoid attributing to the universe. Still, intent is not required for unease. All that is required is coherence where none is expected. The Big Ring's geometry did not just raise eyebrows, it raised methodological questions. Researchers had to ask whether their tools were predisposed to highlight curved alignments, whether clustering algorithms might favor circular arrangements in certain regimes, whether survey boundaries could exaggerate curvature. Every possibility was considered, because every possibility had to be considered. At this level, the difference between discovery and illusion is thin, but the presence of the giant arc complicated dismissal. It was no longer enough to argue that one structure was a fluke. The data now suggested a pattern of anomalies, a suggestion that something systematic might be happening at that scale of the universe. Not necessarily new physics, possibly new limitations. This distinction is crucial. Cosmology does not assume its models are complete. It assumes they are useful approximations. When observations strain those approximations, the first response is not to abandon them, but to probe their boundaries. The Big Ring sat precisely on one such boundary, too large to ignore, too subtle to proclaim, too coherent to dismiss casually. It forced a re-examination of what too large really means, because size alone is not the issue. Distribution matters, geometry matters, context matters. A universe that is statistically smooth can still contain rare extremes. But when extremes appear, structured, curved, aligned, suggestive statistics begin to feel less comforting. The Big Ring did not violate cosmology outright. It did something more unsettling. It exposed how much cosmology relies on expectation. Expectation that structures average out. Expectation that randomness dominates beyond certain scales. Expectation that coherence fades. These expectations are not laws. They are conclusions drawn from models that have worked remarkably well until they meet data that hovers at the edge. The Big Ring hovered there. It did not force a conclusion. It forced a pause. And in that pause, cosmologists confronted an uncomfortable possibility that the universe might allow rare, extreme structures that sit just beyond the thresholds we consider safe. Not common enough to reshape everything, not impossible enough to dismiss, just present enough to demand humility. When the stakes rise in science, certainty retreats. What remains is careful language, repeated tests, and an openness to being wrong. The Big Ring demanded all three. It reminded researchers and anyone paying attention that cosmology is not the art of declaring final truths. It is the practice of negotiating with data that arrives late, faint, and incomplete. Whether the Big Ring ultimately proves to be real or illusory is almost beside the point at this stage. What matters is that it raised the stakes. It transformed a curiosity into a question, and it made clear that the smoothness of the universe, long taken as a reliable guide, may not be as absolute as it once seemed. Not broken, but tested. Nothing about the Big Ring was ever drawn with a pen. There was no moment when an astronomer circled a shape on a screen and said, "There it is." What existed instead were shadows, thin interruptions in ancient light, scattered across thousands of observations. Turning those shadows into a structure required something far more fragile than a telescope. It required interpretation. Every quasar spectrum begins as a line of light split into colors. Within that line are tiny absences, specific wavelengths missing, absorbed by atoms drifting between galaxies. These absences are not dramatic. They do not leap out. They sit quietly, waiting to be counted. When astronomers catalog these absorption features, they reduce the universe to points, each one marking a place where matter once intersected a line of sight. A magnesium absorption system does not describe a shape. It describes a probability that gas exists somewhere along a path, billions of light years long, on their own. These points are meaningless. Only when enough of them are gathered does structure become even possible. But structure is not discovered automatically. It is constructed carefully, mathematically, and with assumptions that are rarely visible from the outside. The first step is selection. Which absorption systems count? How strong must the signal be? Which redshift ranges are included? Which regions of the sky are excluded due to incomplete coverage? These choices matter because the universe you map depends on the universe you choose to include. Once the dataset is defined, patterns are sought, not visually, but statistically. Algorithms test whether absorbers cluster more than expected by chance. They look for correlations across angular separation and redshift. They ask whether alignments persist when the data is sliced differently. At this stage, nothing is labeled a structure. Everything remains provisional. Only when correlations appear consistently across methods, subsets, and thresholds does interpretation begin to solidify. This is where shadows start to resemble shapes. A curve emerges not because someone draws it, but because probability increases along a path. Points appear more frequently where randomness says they should not. The curve gains weight not from appearance, but from persistence. Still, this persistence is delicate. Change the statistical model, and significance shifts. Expand the dataset, and coherence may weaken or strengthen. Adjust the clustering radius, and arcs can fragment or fuse. Every structure inferred from shadows exists within a narrow corridor of methodological trust. This is not a flaw. It is the reality of working at the edge of observability. The universe does not present itself cleanly. It offers fragments, and scientists must decide how to assemble them without forcing the outcome. This is why claims like the Big Ring are framed cautiously. Researchers speak in probabilities, not declarations. They emphasize confidence intervals, not certainty. They describe shapes as ring-like, not rings. Language becomes a safeguard, because once a structure is named, it acquires psychological weight. A ring feels more real than a statistical excess along a curved path. The risk is that the label begins to guide interpretation, rather than the data guiding the label. Turning shadows into structures is not just a technical challenge, it is a cognitive one. Humans are pattern-seeking creatures. The moment data hints at coherence, the brain fills in gaps. It smooths irregularities. It completes curves. Science exists to slow that instinct down. This is why replication matters so much. Independent datasets, independent methods, independent teams. A structure that survives all three begins to earn legitimacy. The Big Ring has not yet reached that status, but neither has it collapsed under scrutiny. It exists in an intermediate state, supported enough to be discussed, fragile enough to be contested, and that ambiguity is precisely where cosmology becomes most interesting, because it exposes the scaffolding behind knowledge. It reveals that what we call structure is often a negotiation between signal and interpretation. Consider how different this is from everyday seeing. When you look at a mountain, you do not ask whether it is statistically significant. You do not test whether its slope persists under alternative definitions. It exists independently of your method. The Big Ring does not. It exists only insofar as the method holds. This does not make it unreal. It makes it conditional. Many of the most important discoveries in astronomy began this way. Dark matter was first inferred from discrepancies, not images. The expansion of the universe was detected through redshifts, not motion. Black holes were mathematical necessities long before they were photographed. In each case, absence spoke before presence. The difference is scale. When shadows imply structures spanning billions of light years, the margin for error shrinks. The consequences of misinterpretation grow. The line between discovery and illusion becomes razor thin. This is why turning shadows into structures demands restraint. It demands that researchers constantly ask whether the shape is in the universe or in the method. The Big Ring forces that question relentlessly. Is the curvature real, or a projection effect? Is the coherence physical, or a product of sparse sampling? Is the structure unique, or an extreme example of something common? None of these questions can be answered with a single dataset. They require patience, they require time, and they require a willingness to accept uncertainty without rushing toward resolution. Turning shadows into structures is not about imposing order. It is about listening carefully enough to know when order might already be there and when it might not. This process is slow, deliberately so, because once a structure is accepted, it reshapes interpretation. It influences models. It alters expectations. It becomes part of the story we tell about the universe. And stories, once told, are hard to untell. The Big Ring has not yet crossed that threshold. It remains a proposal, a possibility, a suggestion traced in absence rather than light. But the fact that it can be traced at all, using nothing more than shadows left by ancient gas clouds, reveals something profound about modern cosmology. The universe does not need to shine to be known. It only needs to interrupt the light just enough for us to notice. And sometimes, when enough interruptions align, they hint at structures so large that even their shadows feel heavy. In everyday life, size is relative. A mountain is large. An ocean is vast. A continent feels almost incomprehensible. But none of these challenge the rules that describe how the world works. They are big, yet comfortably contained within expectations. In cosmology, size is different. At a certain point, how big something is stops being descriptive and starts becoming diagnostic. Size turns into a test, a boundary, a question directed at the foundations of theory. The Big Ring sits exactly at that boundary. To understand why, you have to appreciate that cosmology is not just about cataloging objects. It is about predicting distributions. It asks not only what exists, but what should exist on average, over immense volumes of space. When cosmologists simulate the universe, they begin with tiny fluctuations in the early cosmos, quantum irregularities stretched by cosmic inflation. Over billions of years, gravity amplifies these fluctuations, drawing matter into filaments, sheets, and clusters. This process builds the cosmic web, but it does so with limits. Gravity is powerful, but it is not instantaneous. It works locally. Gradually, structures grow by accretion, merger, and collapse. As scale increases, coherence becomes harder to maintain. At some point, expansion wins. Beyond that point, matter is simply too dispersed, too disconnected, to organize into anything coherent. Fluctuations cancel, patterns dissolve. This expectation is not philosophical, it is mathematical. Cosmologists can calculate the size at which density variations should average out. This is sometimes called the scale of homogeneity. Its precise value depends on how you define smooth, but it generally falls in the range of a few 100 million light-years. That number matters. A structure tens of millions of light-years across fits comfortably inside this regime. Even hundreds of millions can be accommodated as rare extremes. But when you begin talking about billions of light-years, you are no longer at the edge, you are beyond it. At that scale, the universe is expected to behave like a well-mixed fluid. Any large-scale anisotropy should be vanishingly small. This is why size becomes a problem. Not because large structures are forbidden, but because the probability of maintaining coherence over such distances drops sharply. To sustain a curved, ring-like alignment across a billion light-years, matter would need to remember correlations across regions that have never been in causal contact. That last phrase is key. Causal contact means the ability for information or influence to travel between regions. In the early universe, the speed of light and the rapid expansion of space limit which regions can interact. Inflation was introduced precisely to explain how distant regions could share similar properties. But even inflation does not trivially generate late-time coherent structures of this kind. So when a structure appears too large, cosmologists ask, what process could have coordinated it? And often, the honest answer is, none that we know of. This does not mean new physics is required. It means the claim must survive extraordinary scrutiny, because there is another possibility, one far less exotic, but just as important, the possibility that size is being misread. When datasets are sparse, alignment can appear larger than it is. When projection effects are strong, curved shapes can emerge from unrelated points. When survey coverage is uneven, boundaries can exaggerate coherence. In other words, size can be inflated by method. This is why cosmologists do not react to largest known structure headlines with alarm. They react with calculation. They ask how many independent regions the universe contains at that scale. They estimate the probability of seeing at least one extreme realization given enough volume. They test whether the structure persists when definitions change. Only then does size begin to mean something. The Big Ring's reported diameter on the order of 1.3 billion light-years forces these calculations into uncomfortable territory. It sits well beyond the scale where homogeneity is usually expected to emerge. That does not make it impossible, but it does make it improbable. And improbability is the currency of cosmology. Every model predicts distributions, not certainties. Rare events are allowed. The question is whether they are rare enough to be plausible, or so rare that they point to error. This is where emotion often sneaks in. A structure that is too big feels threatening. It seems to undermine hard-won understanding. But science does not operate on feelings. It operates on likelihoods. If the Big Ring is real, it must fit somewhere within the statistical tail of known processes, or force an extension of those processes. If it is not real, then its apparent size becomes a case study in how easily intuition can be misled by data. Either outcome is valuable, because both outcomes teach the same lesson, that scale is not just a number, but a constraint. Cosmology works because it is predictive. It says, given these initial conditions and these laws, you should expect structures of roughly this size, with roughly this frequency. When an observation presses against that expectation, it demands explanation, not outrage. The Big Ring presses hard. It does not break the theory. It leans on it. It tests how flexible it is, how much deviation it can tolerate before assumptions must be revisited. This is healthy. The history of science is filled with moments where too big became the seed of progress. The Milky Way was once too big to be just a cloud. The universe was once too big to be static. Expansion was once too big to ignore. But it is also filled with moments where too big dissolved under better measurement. Distinguishing between these cases is slow work, and that slowness is a feature, not a flaw. When size becomes a problem, it is not because the universe has misbehaved. It is because our expectations have reached their limit. The Big Ring sits at that limit, not as a verdict, but as a challenge, a reminder that in cosmology, numbers do not merely describe the universe, they interrogate it, and sometimes the interrogation itself reveals how much remains unresolved. Every time cosmology confronts something unexpected, the same question surfaces quietly, persistently, and without drama. Is this real? Or is this what randomness looks like when the universe is very large and our data is very limited? The question is not philosophical, it is methodological. And it matters because the difference between discovery and illusion in cosmology is often not visible in images, but buried in statistics. At first glance, the Big Ring and the giant arc feel persuasive. Their reported scales are enormous. Their geometries appear coherent. Their locations overlap in cosmic time. Together, they suggest a universe that may be more structured than expected. But statistics is unforgiving. In a universe that contains trillions of galaxies and an almost infinite number of possible alignments, rare patterns are not just possible, they are inevitable. The larger the data set, the more likely it is that something unusual will emerge somewhere. This is known as the look elsewhere effect. If you search enough parameter space, different distances, angles, thresholds, clustering definitions, you will eventually find something that looks significant, not because it is physically meaningful, but because probability guarantees outliers. The danger is subtle. Once an outlier is found, it becomes tempting to treat it as special, forgetting how many ways it could have failed to appear. Cosmology guards against this by asking a difficult question. How often would something like this appear by chance if the universe were perfectly ordinary? Answering that question is harder than it sounds. You need a baseline, a model of what ordinary looks like. You need simulations that replicate survey geometry, observational limits, noise, and selection effects. You need to know how often random data produces shapes that resemble arcs, rings, or walls, and you need to be honest about uncertainty. This is where claims about ultra-large structures live or die. One of the central challenges is selection bias. Astronomical surveys do not observe the sky evenly. Some regions are studied deeply, others sparsely. Certain redshift ranges are sampled more densely than others. Instrument sensitivity varies. These uneven conditions can create artificial patterns. Imagine shining a flashlight through fog, but only scanning certain directions carefully. You might conclude the fog is denser in those directions not because it truly is, but because that's where you looked hardest. The same principle applies to cosmic surveys. Absorption systems are detected only where bright background sources exist. Quasars are not evenly distributed. Their visibility depends on distance, brightness, and observational strategy. This creates a lattice of sightlines that is anything but uniform. When you map absorbers along these sightlines, the resulting distribution inherits their geometry. Alignments can appear simply because the underlying sampling is anisotropic. Another complication is projection. The universe is three-dimensional, but most surveys project information onto the sky, collapsing depth into redshift bins. Structures that are unrelated in space can appear aligned when viewed from a particular angle. A curve in 2 dimensions does not guarantee a coherent object in 3. This is why cosmologists are cautious with words like ring. The shape may not exist as a closed structure in space. It may be an artifact of how sparse data intersects a curved coordinate system. Then there is thresholding. To identify meaningful absorbers, scientists must choose a cutoff, how strong an absorption signal must be to count. Change that threshold slightly, and the dataset changes. Clusters can merge or dissolve. Shapes can sharpen or blur. There is no perfect threshold, only reasonable ones, and reasonable choices can still produce misleading coherence. Critics of ultra-large structure claims often focus here. They ask whether the structure persists across a wide range of thresholds, or whether it exists only under specific conditions. If a feature vanishes when parameters shift modestly, confidence erodes. Supporters counter that no structure survives all parameter choices. Robustness is relative, not absolute. This back and forth is not a failure of science. It is science working as intended. Cosmology advances not by declaring winners, but by narrowing uncertainty, and uncertainty is unavoidable at this scale, because no matter how carefully you analyze the data, you face an inescapable limitation. You only have one universe. You cannot repeat the experiment. You cannot observe alternate realizations. You cannot average over multiple cosmic histories. This makes statistical inference in cosmology uniquely fragile. You can simulate many universes, but they depend on assumptions. You can generate mock catalogs, but they inherit model biases. You can test null hypotheses, but the null itself is not guaranteed. This is why debates over structures like the Big Ring are not settled quickly. Some researchers argue that the reported significance is overstated, that the structure lies within the expected tail of random clustering. Others argue that its geometry and proximity to the giant arc make coincidence unlikely. Both positions are defensible. What matters is not which side is correct today, but how the argument is framed. Cosmology does not ask whether something looks real. It asks whether reality demands it. Does accepting the structure improve our understanding of the universe? Does rejecting it preserve consistency without introducing contradiction? Does either choice require assumptions that are more strained than the other? These are slow questions. They resist headlines, and they reveal something important about how science deals with ambiguity. In popular imagination, science discovers truth in clean steps: observation, confirmation, acceptance. In reality, science often lives in the grey. Structures like the Big Ring inhabit that grey space. They are neither confirmed nor dismissed. They exist as tensions between data and expectation, between pattern and probability. Calling them statistical illusions is not an insult. It is a recognition that illusion is always a possibility when perception outruns evidence. Calling them real is not a victory. It is a commitment to explaining something that strains existing frameworks. At this stage, the honest answer is not either, or it is not yet, and that answer, unsatisfying as it may seem, is one of science's strengths. Because it resists the temptation to resolve uncertainty prematurely, the universe does not owe us clarity on our timeline. And when patterns emerge at the edge of our statistical reach, the most responsible response is not belief or disbelief, but patience. Sometimes, the hardest thing in cosmology is not seeing a structure. It is deciding whether what you see deserves to be believed. There is a quiet conflict at the heart of every scientific discovery. It rarely makes headlines, but it shapes how knowledge survives scrutiny. On one side stands pattern, the human instinct to connect dots, to see order emerge from noise. On the other stands physics, the discipline that demands restraint, mechanisms, and mathematical accountability. The Big Ring sits squarely between them. Patterns are not mistakes. They are how intelligence begins, long before equations. The brain learned to recognize regularity as a survival tool. Faces in the dark, tracks in the soil, cycles in the seasons. Pattern recognition is ancient, fast, and deeply emotional. Physics, by contrast, is slow. It asks whether a pattern is permitted by laws, not just visible in data. It demands causes, not correlations. It insists that every structure earn its existence through dynamics that can be traced, modeled, and tested. When the two align, discovery feels effortless. When they clash, science becomes uncomfortable. The Big Ring is uncomfortable because it looks like something: a curve, a closure, a suggestion of symmetry. Even when described cautiously, even when hedged with probabilities, the geometry presses against intuition. It tempts the mind to conclude that a structure must exist because a structure appears to exist. But physics is unimpressed by appearance. Physics asks a harsher question: what force could have made this? In the universe, structure formation is not artistic. It is mechanical. Gravity pulls, expansion stretches, matter responds to gradients and instabilities. Every filament and cluster you see can be traced back to these principles, amplified over time. For a structure to be real, it must have a lineage. It must be possible to say, this fluctuation grew into this density contrast, which evolved into this arrangement. Under these conditions, across this span of cosmic time, the Big Ring challenges that narrative. At the redshift where it appears, the universe was still young. Matter had not had unlimited time to reorganize itself. The larger the structure, the harder it becomes to explain how gravity coordinated it without violating causal limits. This is where pattern and physics begin to argue. Pattern says, the alignment is too coherent to ignore. Physics replies, coherence requires a mechanism. Pattern says, it persists across analyses. Physics replies, persistence does not equal causation. Pattern says, there are two of them now. Physics replies, rarity does not imply impossibility or reality. This exchange is not adversarial. It is necessary, because without pattern recognition, nothing would ever be noticed, and without physics, everything would be believed. Modern cosmology lives at the intersection of these impulses. Data analysis tools are incredibly good at finding patterns. Machine learning algorithms can identify correlations no human would ever see. But these tools are agnostic to meaning. They do not know whether a pattern corresponds to a physical process or a statistical accident. That burden falls on theory. Theory does not exist to explain everything. It exists to constrain explanation. It draws lines between what could happen and what merely appears to happen. This is why physicists are cautious about naming. Calling something a ring invites interpretation. It suggests a closed loop, a coherent object. But the data may only support an excess probability along a curved path. The distinction matters because physics does not respond to names. It responds to equations. A ring demands symmetry. Symmetry demands origin. Origin demands cause. Without a plausible cause, the safest position is skepticism. But skepticism is not dismissal. There is a difference between saying this is wrong and saying this is not yet grounded. The latter is far more common in serious science. The big ring exists in that space. It has not been shown to violate physics, but it has not been shown to arise naturally from known processes either. This creates tension, because the universe has surprised physics before. Dark matter was once just a pattern in galaxy rotation curves. Dark energy began as an inconsistency in supernova brightness. In both cases, physics lagged behind pattern and eventually caught up. But history also remembers patterns that vanished. Claims of periodicity in galaxy redshifts, apparent alignments that dissolved under better data, structures that shrank or disappeared as surveys expanded. Pattern alone is not predictive of outcome. What decides the battle is not conviction, but accumulation, more data, independent methods, different traces, replications that do not share the same assumptions. Physics waits for these things, and in the meantime, it applies pressure. If a structure is real, it must survive attempts to explain it away. It must persist as models improve. It must remain when biases are corrected and thresholds adjusted. If it is an illusion, it will fade not suddenly, but quietly as uncertainty tightens. This process is rarely dramatic. There is no single moment when illusion is declared or reality confirmed. There is only a gradual shift in confidence, and confidence in cosmology is earned slowly. The battle between pattern and physics is not about ego. It is about discipline, about refusing to let fascination outrun justification. Because the universe is vast enough to generate endless coincidences, and the human mind is powerful enough to find meaning in all of them. Physics exists to slow that process down. It says, show me how, show me why, show me what breaks if this is true. Until those questions are answered, even the most seductive pattern remains provisional. The big ring has not lost this battle, but neither has it won. It stands as a reminder that discovery is not a moment, it is a negotiation between what we see, what we expect, and what the universe is willing to explain. And sometimes, the most important progress happens not when pattern triumphs over physics, or physics over pattern, but when both are forced to admit how much they still do not know. Suppose the big ring is not an illusion. Suppose the statistics hold. Suppose independent surveys confirm the signal. Suppose the curved alignment persists across methods, thresholds, and traces. Suppose the shape remains when better data arrives and the noise recedes. Then the question changes. It is no longer whether the structure exists. It becomes what kind of universe allows it. If the big ring is real, it does not instantly overturn cosmology. That is a common misunderstanding. Science rarely breaks in one dramatic moment. Instead, it bends quietly, incrementally around new constraints. The first implication would be modest, but profound. It would suggest that the scale at which the universe becomes statistically smooth is larger than we thought. Not infinite, not absent, just farther away. Cosmologists speak of a homogeneity scale as if it were a fixed boundary. In reality, it is an emergent property inferred from data. If a coherent structure truly spans more than 1 billion light-years, then that boundary shifts outward. The universe would still be homogeneous on the largest scales, but not as quickly as assumed. That adjustment alone would ripple through cosmology. Simulations of structure formation would need recalibration. Models would have to accommodate rarer, larger fluctuations. The tails of probability distributions would gain new importance. This would not invalidate the cosmic web, it would complicate it. A real big ring would also force deeper questions about the early universe. Large-scale structure does not appear spontaneously. It grows from initial conditions, tiny density variations, seeded in the earliest moments after the Big Bang, are amplified by gravity over billions of years. If a structure as large and coherent as the Big Ring exists, then those initial variations may have been more extreme or more correlated than standard models predict. This does not mean inflation failed, but it could mean inflation was more complex than our simplest versions describe. Inflation is often portrayed as a smoothing process, ironing out irregularities, but it also magnifies quantum fluctuations, imprinting them across vast regions of space. If certain modes were enhanced, if some fluctuations were stretched or aligned more strongly than rare, giant structures could emerge later as echoes of those early conditions. In this sense, the Big Ring would be a fossil, not of galaxies or stars, but of primordial physics. It would carry information from an era otherwise inaccessible, an imprint of how the universe behaved when it was fractions of a second old. That possibility is intoxicating, but it also demands restraint, because every new implication multiplies uncertainty. A real Big Ring would also sharpen questions about gravity itself. Standard cosmology assumes that gravity behaves uniformly across scales. The same laws that bind galaxies together govern the evolution of clusters and filaments. But gravity has only been tested directly across a narrow range of cosmic distances. On the largest scales, its behavior is inferred, not observed. If matter organizes more coherently than expected over extreme distances, it raises the possibility, however tentative, that gravity's large-scale behavior includes subtleties not fully captured by current models, not exotic forces, not radical departures, just refinements, small deviations that only become visible when the universe is viewed as a whole. In this scenario, the Big Ring would not be evidence of something fundamentally new. It would be evidence that our approximations, while powerful, are incomplete. There is also a more conservative implication. The Big Ring might represent an extreme but allowed outcome within known physics, a statistical rarity that happens to sit near the edge of observability. In a universe as vast as ours, even 1 in a billion events will occur somewhere. If this is the case, the Big Ring would not demand new theory. It would demand humility about probability. It would remind us that unlikely is not the same as impossible. And that the universe does not distribute its surprises evenly. But even this conservative reading carries weight, because it would imply that our intuition about scale has been trained on averages, not extremes, that we have underestimated the size of the universe's statistical tail. This matters because cosmology often leans on typical behavior. Models are calibrated to medians, means, and variances. Rare events are tolerated, but rarely emphasized. A confirmed Big Ring would demand attention to those rare corners of parameter space. It would encourage cosmologists to ask not just what usually happens, but what can happen. That shift in emphasis has consequences. It changes how surveys are designed, how anomalies are treated, how confidence is framed. It moves cosmology from a discipline comfortable with smoothness into one alert to exceptional structure. There is also a philosophical implication. A universe that allows structures like the Big Ring is a universe less tidy than we imagined. Not chaotic, but less eager to conform to simplified narratives. It would suggest that coherence can persist longer, farther, and more subtly than expected, and that the line between order and randomness is not sharp. This does not diminish the success of cosmology. It enriches it, because the strength of a scientific framework is not measured by how often it is right, but by how well it adapts when confronted with the unexpected. If the Big Ring is real, cosmology adapts. It does not collapse. It expands. It becomes more cautious about assumptions, more attentive to extremes, more aware of its own boundaries, and perhaps most importantly, it becomes more honest about what it does not yet understand. A real Big Ring would not tell us everything. It would tell us something far more valuable, that the universe still holds structures large enough, subtle enough, and ancient enough to test the limits of our imagination and the patience of our theories, and that even after a century of cosmological progress, there remain patterns in the sky that do not ask to be explained quickly. They ask to be taken seriously. Suppose the opposite is true. Suppose the Big Ring fades under scrutiny. Suppose expanded surveys soften the alignment. Suppose improved statistics dissolve the curve into chance. Suppose the structure, once so compelling, turns out to be an artifact of method rather than a feature of the universe. Then what? At first glance, this outcome might feel like a disappointment, a retreat from mystery, a return to safety. But in science, the disappearance of an anomaly is not failure. It is resolution, and sometimes it is the more instructive resolution. If the Big Ring is not real, the universe does not become smaller. Our understanding becomes sharper, because what vanishes is not curiosity, but illusion. In that scenario, the story shifts from cosmic structure to human perception. From the architecture of the universe to the architecture of inference, the lesson becomes less about what exists out there, and more about how easily meaning can be constructed when data is sparse and expectations are high. This is not a weakness of science. It is one of its defining strengths. Science is designed to detect its own errors. Every claim is provisional. Every conclusion is conditional. No pattern is sacred simply because it looks persuasive. The willingness to let a compelling idea dissolve under evidence is what separates inquiry from belief. If the Big Ring is not real, then what remains is a clearer picture of the limits of statistical cosmology. It would demonstrate how easily structure can be overinterpreted when working at the edge of observability, where data is incomplete, sampling is uneven, and noise masquerades as signal. This matters deeply, because modern cosmology increasingly relies on massive datasets analyzed through automated methods. Algorithms excel at detecting correlations, but they do not understand causation. They do not distinguish between meaningful alignment and coincidental geometry. That responsibility falls to humans. A vanishing Big Ring would serve as a cautionary example, one that future researchers would study carefully, not to ridicule, but to refine. It would highlight the importance of testing anomalies across independent datasets, of challenging assumptions embedded in analysis pipelines, of asking not just what appears, but why it appears, and crucially, how often it should appear by chance. This kind of introspection strengthens science. It improves survey design. It sharpens statistical tools. It encourages transparency about uncertainty. It reminds researchers that the universe is vast enough to generate convincing coincidences, and that not every beautiful pattern carries physical meaning. There is also a deeper philosophical lesson here. Human beings are meaning-making creatures. We are uncomfortable with randomness. We prefer narratives to noise, shapes to scatter, stories to statistics. When confronted with enormous datasets and abstract spaces, the mind seeks anchors, circles, arcs, alignments, anything that feels stable. The big ring, if illusory, would be a mirror held up to that instinct. It would show how easily the language of discovery can outpace the rigor of confirmation. How quickly a tentative signal can acquire emotional weight. How labels, once applied, shape interpretation. Calling something a ring invites belief in symmetry and closure, even when the underlying data supports only probability gradients. This is not a flaw unique to cosmology. It appears in every field that operates near the limits of detection. Particle physics, neuroscience, climate science. Wherever signals are weak and stakes are high, interpretation becomes vulnerable. The lesson is not to distrust data, but to respect its fragility. If the big ring dissolves, cosmology does not lose credibility, it gains maturity, because each resolved illusion tightens the boundary between what is known and what is conjectured. It clarifies which questions are meaningful and which are artifacts of method, and clarity is progress. There is also something quietly reassuring about this outcome. A universe without the big ring is not boring. It is still vast, still structured, still mysterious. It still contains filaments stretching hundreds of millions of light years. It still harbors dark matter, dark energy, black holes, and cosmic expansion. What it does not contain, at least in this case, is a structure that forces theory to bend prematurely. This allows cosmology to remain cautious rather than reactive. It preserves the integrity of frameworks that have proven remarkably successful across many scales. It reinforces the idea that extraordinary claims require extraordinary evidence, not extraordinary excitement. But perhaps the most important lesson lies elsewhere. If the big ring is not real, it reminds us that science is not about accumulating wonders. It is about refining understanding. Not every anomaly needs to become a revolution. Some need to become footnotes. Others become training grounds, places where methods are tested, biases exposed, and confidence recalibrated. The universe does not owe us surprises on demand, and when it does not deliver them, that restraint is itself informative. It tells us that our models still hold, that our assumptions remain useful, that our expectations, while imperfect, have not yet been outpaced by reality. There is dignity in that outcome, because it shows that science is not driven by the need to astonish, but by the commitment to be accurate even when accuracy is anticlimactic. If the big ring is not real, the universe remains smooth where it was expected to be smooth. But our understanding becomes less naive. We learn to trust data less blindly, patterns less eagerly, and conclusions only after patience has done its work. And in that sense, nothing is lost, because the true achievement of cosmology is not discovering the biggest structures. It is learning how to tell the difference between what is truly there and what only appears when uncertainty is stretched too far. Sometimes, the most valuable discovery is realizing that the universe has not changed, only our interpretation has. By the time you reach the edge of this story, something subtle has changed, not in the universe, but in the way you stand inside it. Whether the big ring endures or dissolves, the journey it forces upon cosmology reveals a deeper truth. The universe does not arrange itself for ease of understanding. It does not simplify itself to match human expectation. It resists clean boundaries, tidy categories, and final answers. And that resistance is not a flaw, it is the point. For centuries, humanity has approached the cosmos with a desire for order, spheres within spheres, laws that apply everywhere, patterns that repeat cleanly across scales. Each step forward, each successful theory, has reinforced the hope that, given enough data, the universe would eventually become transparent. But transparency has limits. The deeper we look, the more the universe reveals a personality that is neither chaotic nor perfectly ordered, something in between. A place where averages behave beautifully, while extremes quietly undermine certainty. The big ring, real or not, exists at that boundary. It is not an answer. It is a pressure point. It presses on assumptions that were never guaranteed. It presses on the confidence that smoothness emerges quickly and reliably. It presses on the idea that scale alone determines simplicity, and in doing so, it reminds us that cosmology is not a completed map. It is an evolving conversation. Living in a universe that refuses to be simple requires a particular kind of humility. Not the humility of insignificance, but the humility of participation. You are not an external observer peering in. You are embedded within the system you are trying to understand. Your measurements are constrained by light speed. Your data is filtered by cosmic history. Your interpretations are shaped by cognition, evolved for survival. Not for billion-light-year abstractions. This does not make knowledge impossible. It makes it provisional. Every cosmological model is a compromise between elegance and evidence. Every theory carries assumptions that work until they don't. And when they don't, the universe does not apologize. It simply presents new data. There is something deeply human about how science responds to that presentation. First comes surprise, then doubt, then debate, then patience, rarely certainty. The story of the Big Ring, whether it becomes a confirmed structure or a resolved illusion, fits this pattern perfectly. It shows science not as a machine that produces truth, but as a discipline that manages uncertainty. And uncertainty is not weakness, it is the space where understanding grows. A universe that refuses to be simple demands better questions. It forces us to examine not just what we observe, but how we observe. It teaches us to separate expectation from evidence, pattern from process, meaning from coincidence. This is not comfortable work. It is far easier to believe that the universe conforms neatly to our frameworks, that anomalies are either revolutionary or irrelevant. That complexity eventually gives way to clarity. But reality is rarely that obliging. Instead, the universe offers gradients rather than boundaries, probabilities rather than certainties, structures that exist not as objects, but as statistical tendencies. Learning to live with that ambiguity is part of scientific maturity. It is also part of human maturity, because the questions raised by cosmology do not stay in the sky. They echo inward. They challenge how we think about knowledge, meaning, and our place in something far larger than ourselves. If the universe is not perfectly smooth, what does that say about our desire for uniformity? If patterns emerge where none were expected, how much of meaning is discovery and how much is projection? If certainty is always provisional, what does it mean to claim understanding? These are not questions with equations as answers. They are questions that change how you listen to science. A universe that refuses to be simple is not hostile. It is honest. It does not promise comprehension on human timescales. It does not guarantee closure, but it does offer participation. Every anomaly invites investigation. Every unresolved tension sharpens tools. Every failed claim improves method. Progress does not come from perfect alignment between expectation and reality. It comes from the friction between them. The Big Ring exists in that friction. It may one day settle into the catalogue of cosmic structures, or it may dissolve into the archive of instructive illusions. Either way, it has already done its work. It has reminded us that cosmology is not about collecting wonders. It is about cultivating restraint, about knowing when to pause, when to question, and when to admit that clarity has not yet arrived. And perhaps that is the most important lesson of all. Living in a universe that refuses to be simple does not diminish wonder, it deepens it. Because wonder grounded in humility lasts longer than wonder fueled by certainty. When you look out into the night sky now, you are not just seeing stars and galaxies. You are seeing the outer edge of a conversation, one that began long before Earth existed and will continue long after. A conversation shaped by light, by distance, by probability, and by the stubborn complexity of a universe that refuses to be reduced to a single story. And within that complexity, there is room for patience, room for curiosity, and room for the quiet understanding that not knowing everything is not a failure. It is the condition that makes exploration possible.